All right, so we're going to be taking a look at how we find this derivative, and I'm starting us off with one of them that tends to be the toughest, because when we first look at this, we might think we don't even need chain rule, because that to the power of 5 sitting in the middle is just kind of awkward there. And so the first thing that I would suggest is that we actually write this original function here in an equivalent form that makes it a little bit more obvious about what the inner and outer functions are. Those two statements are equivalent. And so now it makes it a lot easier to see that our inner function is sine and our outer function is something to the power of 5. And so I can now jump in and start finding my derivative. So t prime of x here is going to be 5 times the exact same thing to the power of 4. And so whatever that inner function is, that's what gets plugged in here. So that's still going to be sine of x inside of there. It's just that then I have to multiply it by the derivative of that inner function. So the derivative of sine, of course, is cosine. And so that would be our derivative. Now, having done that last one, this one will probably seem a little bit more familiar, a little bit more comfortable. So for doing this one, we're just going to be able to go straight to the derivative. And thank goodness, because before we learn chain rule, we would have to have done this one by actually multiplying out this 2x cubed plus 5 times itself 4 times and expanding our polynomial. Now, you still can do that, and then you'd just be using power rule, but why? Chain rule is so much simpler, right? And so I'm going to be doing 4 times the exact same thing cubed, so my 2x cubed, I'll even write that as it's in a different color here, just to make it clear where that inner function is coming into play. And then I got to multiply that by the derivative of the inner function, and so the derivative of 2x cubed is going to be 6x squared, and then the derivative of 5 is 0, so that just goes away. And so then this is our derivative. Now, technically, this is the derivative and done, but there's some really straightforward simplification to be done. So yes, let's do that simple simplification. Some of the more complex stuff, I'll be like, yeah, we can skip that. But here, all I got to do is do 4 times 6. And then maybe write the x squared before I write the parentheses. It's a very small step to make a big difference in what that simplification actually looks like. So, do it. All right, so for this one, we can go straight to our derivative. After having done last night's assignment even, it probably is a little bit more natural because you had one that was kind of similar to this last night where we had to do derivative of secant. Remember, the derivative of secant is secant tangent. And normally it's secant tangent of x. In this case, it's going to be secant tangent of 3x. And so I go ahead and plug that 3x, my inner function, into both. And then remember, I'm not done yet. I still have to multiply by the derivative of that inner function. So I'm going to multiply by the derivative of 3x, which is just 3. Now, if you wanted to, that means you could just very quickly simplify it and turn it into 3 secant 3x tangent 3x. And that would even be the fully prettied up version, all simplified and put in a nice order. Can you imagine trying to do this problem without chain rule? I mean, it's possible. You could actually multiply that thing out 100 times, but boy, would that be a pain. So fortunately, we can use chain rule because we have our inner function here. And so I'm going to do straight to r prime. So r prime of x is going to equal, and we're just going to use power rule on that outer function. That's the something to the power of 100. So we're going to go 100 times that same something to the 99th power. And then I just plug that inner function in, so 4x minus x squared, and then I multiply that by the derivative of the inner function, which is going to be 4 minus x. Oops, minus 2x, sorry, forgot about the 2. There we go. And that's it. Yes, we could clean it up. I'm not going to really worry about it too much in this case, but that's all we got to do. All right, and so again, this is another one where we're going to have to use chain rule. Because it's not just tangent of x, it's tangent of this other stuff. So anytime it's not just the x in there, we got to use chain rule there. So we're going to now go to finding out what p prime is. And so the derivative of tangent, secant squared, of whatever was our inner function. So that's going to be of the cosine of x plus 5. Remember, it's not touched. I'm not doing anything to that function when I'm taking the derivative of the outer. I just plug it in as it was. And then I multiply that by the derivative of that inner function. So the derivative of the cosine of x, that's going to be negative sine of x. And the derivative of the 5 is 0, so that's my whole derivative right there. If you want to clean it up, you could, but the only cleanup we can do in this case would be writing it as like negative sine x, and then the secant squared of the cosine plus 5. That'd be about all you could do simplification-wise. All right, now again, the first thing we need to do is figure out what's our inner function, what's our outer function, and sometimes with these exponentials that can be a little bit harder to tell. A way that you can know is that normally when I'd be looking at an equation like this that involves e, normally it'd be e to the power of x, and I know the derivative of e to the x. But it's not e to the x here, it's e to the power of something else. That something else then must be the inner function. So whatever is in the place where x would normally be, that's your inner function. So I now can go ahead and start taking my derivative here. So n prime of x here is going to be, first of all, derivative of the outer function. The derivative of e to the x is e to the x. So in this case, it's going to be e to the power of sine x. Same thing, right? But of course, this one is not its own derivative when we're all done, because I still have to multiply it by the derivative of the inner function. In this case, the derivative of sine. So then it's times cosine of x. And then this is the final answer. So you'll notice the derivative of e to the x, yes, is itself. But as soon as that x becomes something else, it's no longer its own derivative, strictly speaking. There's going to be an extra layer or an extra wrinkle to it. All right, I'd now like you to find the derivative of both of these functions, please. All right, so for this first one, we're going to be doing g prime of x here. And first of all, what's the derivative of 1? 0. Okay, so now I'm going to be doing the derivative of negative sine squared of x. Now, it might help you to first write that as negative sine of x squared. Because remember, that's what that really means there. All right, so in order to find the derivative of that then, I'm going to have to do negative 2 times my inner function. It'd be to the power of 1, but of course I don't need to write to the power of 1. And so that's going to be sine of x there, but then times the derivative of my inner function. So the derivative of sine, of course, is cosine. So why am I writing sine then? Must have it on the mind. All right, and so then I do want to clean that one up. So I end up with g prime equals negative 2, just getting rid of the parentheses, sine cosine. All right. All right, now for the second one, cosine squared. We're going to go ahead and go straight to g prime of x here again. But like the last one, if it's a little bit easier for you, which I can see it definitely being easier, is write it as cosine of x squared. And so in order to find that derivative, I'm going to be doing 2 times my cosine of x. Actually, I'll put that in parentheses for consistency. Cosine of x to the power of 1, so it's just cosine of x. And then that's times sine of x. Wait, there's something wrong there. What's wrong? Yeah, negative sine of x, because the derivative of cosine is a negative sign. So I'm going to want to put parentheses around that to be able to keep track of it. If I don't put parentheses around that, it's going to look like I'm subtracting the sign instead. All right, then again, I want to clean it up, and so I end up with a negative 2. I'll write the sine first just because it's a matter of habit for me, and then the cosine. All right, so those are our two answers. And what do you notice? Yes, they are the same, right? Notice here, negative 2 sine cosine, negative 2 sine cosine. Why are they the same? Yep. Notice 1 minus sine squared, the trig identities for that says that 1 minus sine squared equals cosine squared. So as we just proved that whichever form it's in, you're still going to get the same derivative. Proving once again that the trig identities, yes, identities mean they are exactly the same. So good. Last problem. Going to make you read a little bit here. All right, so let's dig into this problem. Of course, it is a word problem, and so we're going to need to be able to figure out what the words are telling us to do there. So for this one, we're told the height of the tide, so that's what this is talking about then. This is a height function as we take a look at it. Where t is hours since midnight, so remember that's what t is going to mean, it's hours since midnight. So how quickly is the tide changing at 6 a.m.? Well, the biggest thing to note here is that we're looking for how quickly it is changing. Changing means that we need to know what is the rate of change. Rate of change means derivative. All right? So whereas when we talk mathematics, abstract math, we always say derivative correlates to tangent line. When we talk real world, that means derivative correlates to rate of change. It's just how quickly something is changing. And rate of change, derivative, that means I now need to figure out what's the derivative of this function. So let's go ahead and jump into finding our derivative. So we're going to do h prime of t here equals, the 5.4 can just kind of hang out front here. And so I'm going to be doing times the derivative of sine of something. So the derivative of sine, of course, is cosine. So that's going to be cosine of our something, our inner function. And so our inner function in this case is that. It's going to be this whole 24 pi over 149 t. And yes, we do need to keep track of all of that stuff. All right, so then I need to multiply that by the derivative of the inner function. Now, in that inner function, this whole 24 pi over 149, notice that's just a constant. And so this is going to work the same way as if it was 2t or 5t or something like that. The derivative of any constant times t is just the constant. So this is going to be times 24 pi over 149. So there's our derivative. So that tells us how quickly something is changing at any given time. But in this case, I have a particular time I'm interested in. This is going to be h prime of what? 6. Yep, because it is 6 a.m. and 6 a.m. of course is 6 hours after midnight, because that's how t was defined. All right, so plug in that 6 and then please calculate out what that answer would be. Now when you do this calculation, should your calculator be in degrees or radians? Yes, radians. If you didn't think to check that first, take a moment, make sure that you are working in radians here. And so then when we plug it in here, we end up finding that h prime of 6 equals about, because this is definitely going to end up being rounded, this is not a value that we can just know from the unit circle, negative 2.72. I'll just round it to 2 decimal places here. But this one's actually in context here. So I don't want to just stop at the number. I want to include units. So let's talk what our units would be. Notice that this is h prime of t. If I think about this in terms of that d over d notation, that would be like I'm finding dh over dt. Why would I mention that? Because if you think about it in those terms, it tells you what your units will be. Because the h on the top is measured in what? It's measured in feet. The t on the bottom is measured in hours. And so then that tells me how to know what my units are. So this is going to be negative 2.72 feet per hour. Now, why would it be negative? What's that tell us is happening here? Yeah, it tells us the tide, the depth here, is going down. And so it's actually decreasing. So the tide is going out at this time. And it's going out at a rate of about 2.72 feet per hour.